This is SolidityATL's Web3 Security Session 2. The agenda for today is we're going to talk about the Ethereum virtual machine, as well as some Solidity programming concepts, as well as some Solidity smart contract specifics. And then lastly, we're going to finish off with deployments. In the first module, we're going to talk a lot about the EVM. We're going to dive into virtual machines, the Ethereum virtual machine, nodes, and then gas. Now we're going to also discuss EVM's history. So as many of you know, the first white paper was published by the founder Vitalik in 2013. Fun fact, this was out of spite of his World of Warcraft character being nerfed. For those of you who are not gamers, when your character is nerfed, it basically means the owners of the game have decreased the power of whatever it is your character can do in that game. So Vitalik decided that he was going to create a decentralized ecosystem where essentially you have control of your assets. It's kind of crazy to think that this is how Ethereum was founded, but this is his origin story. The additional founders included Charles Hoskins, Gavin Wood, Anthony Delorio, and Joseph Lubin. Shortly after Vitalik posted this white paper, these members were brought into the Ethereum Foundation to help build what Ethereum is today. Now, the first block of Ethereum was mined in July of 2015. Really want to stress the term mined. When Ethereum was first released, it was a proof of work chain, and now it is a proof of stake chain. So that is a really important thing to understand about EVM's history and just where we are today.
Before talking about the Ethereum virtual machine, I wanted to first cover what a virtual machine is in the first place. So by definition, a virtual machine is any compute resource that uses software instead of the physical computer to run programs and deploy apps. All of us are familiar with computers in different forms, whether it's a desktop, mobile phone, a laptop, or an appliance like a washing machine. Each of these computers will have some type of operating system. For example, Windows, Linux, Mac OS. And the purpose of the operating system is to control the underlying hardware on the computer. So that's where all the drivers are for controlling everything on the computer. The next stage there's something called a hypervisor. Not going to go into too many details about that, but for the purpose of this lesson, a hypervisor, essentially you can think of it as a virtual machine manager. So for example, if you had a Windows computer, but you wanted to run a Windows or a Linux virtual machine, or running a Game Boy emulator or something, you would need a hypervisor to do that. And so lastly, some examples of some virtual machines from other sources. So if you're familiar with Node.js, the V8 engine is a virtual machine because it does abstract away the hardware, and so you can control OS threads, interface with hardware on a PC using V8. In the Java ecosystem, there's the JVM, which is the Java virtual machine. And in Ethereum, it's the EVM, Ethereum virtual machine. So that's what we're going to start talking about now, is diving into the Ethereum virtual machine. Now, to introduce the EVM, the Ethereum virtual machine, one common thing between virtual machines is the concept of volatile memory and non-volatile memory. And this starts to be important in the Ethereum virtual machine, and where the data is actually being stored and accessed. So volatile memory is memory that is being used by a computer program at runtime or in real time, but whenever that virtual machine turns off, that memory is gone. So examples of this are if you've ever played a video game on a desktop or mobile, and whenever you closed out the game, if you didn't save anything to disk, there's nothing saved there. So all the memory like that was used when that game was running was cleared out when you closed it. Another example is different browser states. So if you're doing something on a website and then you close out the browser and go back to that website, a lot of times it's like you never went there before. In terms of programming, examples of this are, like I mentioned previously, with V8 and Node.js, and JVM. Most programming languages, their virtual machines have a concept of volatile memory as well. Non-volatile memory is permanent, meaning that even if the virtual machine is off, then that value will still be there. Examples here are like the file system in your computer or phone. Like you can restart your computer and restart your phone, but your pictures will still be there or other files. Databases are another example of non-volatile memory, where databases can be on a machine that goes out and it goes out of power, but they turn it back on 2 weeks later and all the data is still there. So what it is showing now is a simplified view of the Ethereum virtual machine. Notice here that it's mentioning the word volatile, so that is in the context of volatile memory. And non-volatile memory in this case is persistent, meaning long-term storage. So in this case, the volatile memory in the EVM is the volatile things are the call stack. So this is when the code is actually executing, the call stack is volatile. So like whenever a transaction is done, whatever call stack was there would be cleared. And also the memory in a contract. So if you use the memory keyword, anything stored in memory will be deleted after the transaction is over. The non-volatile memory or persistent areas is storage. So this is the area in contracts where the memory and the data lives on between transactions. Another persistent or non-volatile area is the account state. So that's things like account balances, other things like that. And also the actual EVM code of the contract that's being run is persistent as well. The Ethereum protocol created the Ethereum virtual machine and was the first implementation. Since then, there have been many other protocols that also use the Ethereum virtual machine to operate. So one simplified way to think about the Ethereum protocol is a continuous, uninterrupted state machine that is being controlled by thousands of connected computers called nodes that are running special software called Ethereum client. And we're going to talk about it in the next few slides, but these Ethereum clients are these nodes are computers that are running implementations of the Ethereum virtual machine. So this is where when you actually are creating a transaction, your computer is interacting with these nodes to update the state of the Ethereum chain. Here's a slightly more detailed diagram of the Ethereum virtual machine, adding a bit more to what the previous image we showed was. Before going into more detail here, I do want to mention that these images are directly from the Ethereum documentation. most of the content in this session. You can find a lot more details about each topic here. So I encourage you to take some time to go through these documents if you have questions or want to better understand how things are working underneath. So now I wanted to shift the focus away from memory to gas. And as we start talking about nodes, I first wanted to talk about gas. So in the context of a transaction, one of the first things that gets determined is the gas that's available for that transaction. So that will be things like, what's the gas limit for a transaction? Meaning how much gas is someone willing to pay for a transaction to execute? What's the block gas limit? So for a given block, how much gas does it have before it runs out? And one concept I want to introduce here is that every operation in the Ethereum virtual machine consumes gas, whether that be reading data or writing data or executing functions. We're going to look into opcodes later in this lecture, but just introducing that concept of whenever code is executed in Solidity, there is a gas cost associated with it. I really like this image to illustrate what's happening when you're interacting with a blockchain network. So in the case of a transaction that you're using your wallet for, or you're interacting with a dApp, your transaction is being sent to a node, and that node is running an instance of the Ethereum virtual machine through one of the execution clients, and that is what's actually processing your transaction and then making updates to the network. And then there's other nodes that handle validating that transaction looks correct. And yeah, I think this picture is just very helpful in visualizing what's happening. The two different node client types that every node on Ethereum protocol has to run is the execution client. So this is the client that's actually running an instance of the EVM. This is what's listening to new transactions and holds state data, like account data, storage data, those type of things. The consensus client is purely focused on the proof of stake consensus algorithm on Ethereum. Both the execution client and consensus client have multiple implementations in different languages. The most common languages used for node software is Rust and Go, usually. And one of the advantages of protocols launching EVM compatible chains is they can reuse existing client software. So some of the common execution client software or clients is Geth by far, which is a Golang implementation of the EVM. There's also a new one called Wreath, which is a Rust-based. You can see Open, Ethereum, and these others. And on the consensus client side, there's also multiple implementations written in different languages. One of the risk that comes with any protocol is centralization. And on the protocol level, one of the areas that can appear is in the diversity of node clients. So you can see for Ethereum, what you're seeing here is the distribution of execution clients on the Ethereum protocol. So 83% of Ethereum nodes are running Geth client. So what would happen if someone found a bug in Guest, or there was a malicious actor who was able to take advantage of that monopoly? This is one area where security wise it's good to start thinking about what are the centralization risks and why this is a risk as well. Another way that the centralization risk appears that's not necessarily 100% detrimental but still can be an issue is if a large number of the nodes are running in AWS, for example, and AWS has an outage, or instead of running the nodes directly, a lot of people will use cloud providers like Infura or ChainStack, and sometimes they have outages as well or issues with their nodes, which can cause issues for deploying transactions or just having network access. Same thing with interacting with test nets. If there's no nodes properly functioning on a test net, sometimes you might have a test net go down as well. Another centralization risk on proof of stake chains that we slightly touched on in the last session, but return to here, is the centralization of the stakers. So what you're seeing here is a screenshot from a Dune dashboard, which is showing the distribution of Ethereum validator stake and where they're staking. Here you can see that Lido, which is a decentralized staking platform, takes up almost 33% of where staking is occurring. You also see places like Coinbase and Binance, other centralized places. There's also some self-custodial staking there as well. The risk here is what happens if Lido gets hacked. How would that affect the validator, the Ethereum's ability to validate transactions? What if there was a bug introduced in any of these, like Lido or Coinbase, their staking platforms? How would that impact it? So just being aware that every protocol, even Ethereum, Bitcoin, there is some centralization risk, and being able to recognize that can sometimes help when thinking through different security things. Gas is one of the key concepts in both Ethereum and any blockchain system. Gas is the unit of the amount of computational effort required for an operation to be executed. In a Web2 world, whenever you want to execute code, say in a cloud environment like Amazon or Azure, Google Cloud, you'll often pay a monthly plan, or you can be charged per call, but usually you're charged for the amount of CPU and RAM you're using. In the case of Ethereum and other blockchain protocols, you are charged gas on every transaction, and the cost of every transaction is determined on what's happening in that transaction. Gas fees in Ethereum and EVM chains are required to be paid in the native currency. So if you're ever wanting to do a transaction on an Ethereum protocol, whatever gas that comes associated with it, you have to pay with Ethereum or Ether, which is the native currency. The units for gas are Wei, and different sizes of Wei. So GigaWei would be, I believe, 10 to the 9 Wei. And so different instances of gas are base fee. So for a transaction to occur, how much gas will it cost for a node to execute. Priority fee, there's a max fee, all these different gas fees for figuring out how much a transaction will cost. Similar to many other virtual machines, Ethereum has a set of opcodes. If you've ever heard of or worked with assembly or worked with the JVM or other virtual machines, the concept of opcodes is pretty similar, with the difference being that EVM opcodes have a gas associated with them. For those of you who aren't familiar with an opcode, when you write Solidity and compile your code, the output of that is a set of opcodes on how the Ethereum virtual machine will actually execute. So Solidity is an abstraction on top of these opcodes. From the node's perspective, this is what the node is actually doing under the hood whenever it's executing a transaction on a smart contract. Every opcode has an associated amount of gas. I really like this tool called EVM.codes, where it shows all the opcodes in the Ethereum virtual machine. So some of the simple ones like addition, multiplication, subtraction, and you can see the gas and way. And here you can see all the opcodes that exist. So for example, if you wanted to make an external call, there's the call code. If you want to do delegate call as well, create is called when you deploy a new contract. And you can see that deploying a new contract costs a lot of gas compared to, say, calling another contract. So this EVM.code tool is very helpful if you're ever wondering how much different opcodes will cost, and just to have a list to go back to outside of the Ethereum yellow paper. What we're looking at now is the Geth client, the execution client that showed earlier, that makes up about 80% of all the execution clients on Ethereum network. It's open source, like most of the clients are. And if we navigate into the virtual machine, so in core, there's a section called VM for virtual machine. And inside of here, there's an instructions file here. And you can see this is where the actual opcodes are implemented in the execution client. We're just looking at it on GitHub, and so you can scroll down and you can see all of the same opcodes here that you see on the EVM codes here. So if you're ever curious what's happening under the hood of a node when you're executing things, you can actually go and look at it on GitHub.
About module 2, which is Solidity and programming concepts. So we're not going to dive deep into the Solidity specific things. We're going to cover where does Solidity and traditional programming concepts merge. So we're going to talk about common primitive types, control structures, visibility modifiers, and interfaces. All right, so Solidity is a high-level statically typed programming language designed for writing smart contracts on the EVM. I believe we covered this, but a smart contract, again, is essentially a program. It's a program that allows you to perform different actions and different transactions on a blockchain network, specifically on Ethereum. So I said it's a high-level language. Now, Solidity also, not Solidity, but the EVM also has a low-level language you can use to create smart contracts. This is referred to as YUL. Now, contracts in Solidity are similar to classes in object-oriented languages. Contracts also support inheritance, libraries, various complex and user-defined types, as well as many other features that you will find in traditional programming languages. Now, as we continue on, we won't really have a lot of visuals. We're going to jump into the code and kind of explain these Solidity specifics as we step through each of these different objects we want to cover. So the value types, we have booleans, integers, byte arrays, and string literals, as well as enums. Solidity supports all of these. And we can take a look in Remix. We're going to look at this contract here. This is going to be what you all will be using as your homework assignment. So we're not going to dive too deep into what's happening, but we are going to cover this contract at a high level. So again, you have the ability to have different variables. You have your string variables. We have uint 256. So when we're describing a number or initializing a number, we use uint 256 or uint. You can just use uint, or you can use uint 8, uint 32. So basically, for those of you who understand what's happening here, it's just saying that you have 256 bits that you're going to be able to store in this variable. So when you're using numbers or any type of, when you're working with any type of number, you're going to use either uint or int. And so also just to kind of work our way down here, believe we talked about booleans. So we're going to go into this contract here. This is how you create a boolean here. And we don't have enums in here, but they work similarly in many other programming languages. We won't go through enums, but I will go through another way to use a string. So we have string right here. You can also use bytes, and then you can say message. So that's how you would use bytes. Okay. So Solidity also uses reference types or supports reference types such as arrays, mappings, and structs. We will take a look at that here. So this is how you define a struct. And there are many ways you can initialize a struct after you define it. We can jump down to here. So if you wanted to initialize a struct, you would just use use how you define it, and then throw in those parameters that you have for that struct. All right, next we have arrays. So right here, we define our type, and then we can create our array, but also if you just wanted to create, let's say, a array of numbers, you would do something like this. This would be a dynamic array of numbers because we're not specifically saying how many values or how big our array is going to be. So that's how you create an array. What else do we have? And then mappings. So mapping, for those of you who are familiar with dictionaries, such as like a key value pair, what's happening here is we can create a dictionary or a mapping where we have an address that refers to a integer. So key would be the address, the value would be an unsigned integer. Solidity also supports control structures, which is what you would typically see in most programming languages. We have if-else loops, we have while loops and do-while loops, for loops, return statements, try-catch statements, and hoisting. I'm only going to cover if-else, for loops, return statements. You will see while loops and do-while loops used. You will see try-catches used and hoisting also used. But traditionally, when I'm auditing smart contracts, you don't really see too many of those. The things I mainly see is if-else, fors, and different return statements. Robert may have some more to add to that, but and he may go through while loops and do-while loops as well as the other ones that I don't cover. But let's take a look at what we will typically see in a contract. So this is a function. I have it called increment even numbers. And essentially what this does is if it's an even number, it's going to hit this for loop tree, and then if it's not an even number, it's going to just set number to be equal to 3. So this is how you would do an if-else statement. Not too different from those of you who are familiar with something like JavaScript, and as well as a for loop. Some of these things are almost similar. So if you are jumping from another programming languages into Solidity, it's really not going to be too difficult to pick up. If you are starting off with programming, we do have some assignments for you involved in doing crypto zombies. Even if you're someone who's a programmer, doing crypto zombies is going to be where we're going to assign you as your first few homework assignments so that you'll just get the feel of what it's like to program in Solidity. About visibility modifiers. Essentially what a visibility modifier is, it allows you to specify your visibility or who can see or who can use that specific code. And let's not just talk about it, let's look at the code. So when we say visibility modifiers, if we look at public, let's go to a public function. All right, so if you were to create a function, all this does here is pushes some values to an array, and then sets this new array to this old array, and then performs some type of modification to it. And then lastly, it returns this random array of numbers. So when we look at this function and we see it's public, this means that anyone can call this function, right? We don't have any visibility modifier on it that's labeled private or internal. You pretty much, and actually, if you had that as private, only the contract can look at this function. The contract can use or see what this function is doing, right? But if it's public, or actually let me rephrase that. If it's private, you can't call this. And if it's public, you can. Okay? So when you see something like that, let's look at internal. Similar thing where only this contract can use this function. If you tried to call this function add to number, you would not be able to. This is an internal function. Only this contract has the visibility to use it. Now, I don't want to confuse people to say that if something is private in a contract, you could never see it. Blockchains are open. They are decentralized. You can modify, I won't say modify, you can see the storage of a contract, right? So if I were to put a secret message and store this, and I'm putting the visibility modifier private, this does not mean this message is private. Someone could literally take the storage of a contract and inspect that and see that, okay, I can see what this message is. So don't just think that if you make something private, it's actually a secret. It is not. There's no such thing as secrets in terms of a blockchain. Now, if we want to talk about ZK proofs and zero knowledge stuff, then that would be more towards holding secrets. But on what we're learning here, when we're creating smart contracts, you cannot hide anything from somebody. I believe that's all of them. We have view functions, so maybe we should just create a simple view function. So let's say I wanted to view the number. I want to view what this number is, right? We can just say function view number, and we can say public view turns uint, and all we would do here is say return number. Okay, so the reason why we can make this a view function, this means that you are only reading data. You're not making any modification to anything. Now, if I wanted to say number plus 6, number equals numbers plus 6, right? I'm going to get an error. because I've declared this as a view function. I've declared this with the visibility of only being able to view. I didn't specify the ability for this storage or data to be modified. So that's what the view visibility modifier means. You are only reading data from a smart contract or reading data from the blockchain. So the last thing we're going to go through in this module is inheritance. So for those of you who don't know, inheritance is when you're able to use another contract inside of a new contract. So I know that sounds a little confusing, but let's take a look at it here. So we have our Easy Store contract that we're familiar with, and then we have this ownable contract. So if I want my Easy Store to use some of the storage and the functions that's involved with this ownable contract, the way I can inherit it is by saying Easy Store is ownable. Now, all of the data will be stored in this Easy Store contract, but the thing here is that it's inheriting the functions, all of this stuff inside of Easy Store. So that's what inheritance is, and there are alternate ways that you can inherit things. So let's first talk about abstract contracts before we go into interfaces. So an abstract contract is essentially just a contract that you're not implementing. It's a way for you to create function templates, but you don't actually apply them. So if I wanted to make an Easy Store abstract contract, what I would do is create, for instance, let's take this first function. What I would do is I'd have this set number function. This is where the implementation is going to be, but the actual template of this would be in another contract. So if we let's actually show this example here. Let's create a new contract, and we're going to say Easy Store abstract .sol. You would do everything you need to do here, but what you would do is say abstract contract and then name it. Okay. And obviously we need our identifiers. We'll go into this in a second, but we have our abstract contract and then we have our function. And all you would do here is create the template for that. So that's all an abstract contract is. It's just a template to set up your main contracts. Many people who come from object-oriented programming languages are used to abstract contracts and using this templating format. But if not, it's okay. Sometimes developers don't use this method to create their contracts. It's just a great way to template it out. So next we're going to talk about libraries. So libraries are just a way for you to inherit or use reusable blocks of code. So the way you would inherit a library is a little bit different. You would create it like a similar contract, but you would just rename this to library. Okay. We're not going to change this, but that's how you create a library, similar to a contract. But instead of actually inheriting it using the is keyword, you would import your library. Okay, you would just import that as, so right now we're importing this to use it as a contract, but if we want to import the library to just use it, to import it as a dependency and then use it in our code, that's how we would do it. Okay. All right, and last is interfaces. So an interface is essentially just a way for developers to create chunks of code that allows it to be reusable. So what I mean by that is if I want a smart contract to call another contract, I may use an interface instead of actually pointing my contract to another contract. So That may sound a little confusing, but let's look at a quick interface we created for just this challenge. And what we would do here is create an interface named setNumber. And the way I would use this in my contract, if I was a developer who wanted to interact with the EasyStore contract, all I would do is use this interface, take the contract address, and then point my interface to whichever function or whichever specific interface I'm going to be using. So you have your main interface, but you may have different functions that you want to call. So that's how I would call this, instead of having to worry about the actual functionality within the code. So this is a great way to call other contracts if you don't want to necessarily understand all of the things that's in that function. As a developer, you may have a long and built out function, and you may expose just an interface to the community, to the public, so that way they can easily integrate within your dApp. Okay, and that's everything about inheritance. Module 3, we're going to talk more about some Solidity specific concepts. So remember, in the last module we covered general programming concepts, but we want to talk about these Solidity specific concepts. So we're going to talk through more Solidity primitives, some events and errors. We're going to talk a little bit about gas and loops, some contract modifiers, and then memory location. All right. All right, so the first thing we're going to walk through in this module is progmas and license. So this is something that's specific to Solidity. Your license identifiers clarify what levels of copyright your source code falls in, whether it's MIT, which is usually open source, and if it's unlicensed, it's going to be closed sourced. And then your progmas are Solidity compiler versions. From a security standpoint, it's just best to know that fixed progmas are the most secure. The reason for that is because if you have a floating progma, you may compile your project into a versioning that may have some bugs. So let's take a look at what I'm talking about here, and let me zoom in. We're specifically talking about this section right here. So we see how we have the SPDX license identifier. We have it as MIT, so anybody can use this code. And then we're using progma Solidity 0.8.20. Just to take a look at some of these compiler versions. The latest is 0.8.21. So as you can see, some of these older compiler versions is what you would use back in the old days of Solidity. And with each update comes new functionalities and bug fixes. All right, the next thing to learn is the difference between storage and memory. Memory is a keyword to store data temporarily in a smart contract, and storage is a keyword to store data permanently in a smart contract. So we're going to take a look at an example to really understand the differences between these two. Let's zoom in a little bit. So as I said, memory is temporary. After this function is ran, that data store, that memory, is lost. This is not persistent. The function runs, and the memory data store of new array is going to be lost. Right? And then for storage, after this function is ran, the memory store for new array is going to be persistent. It's going to be kept up after this function. So we're going to have two different challenges you're going to see in the CTF for the homework. You're going to see that there's going to be some interesting feedback from this function or from the smart contract after you run each of these functions. I'm going to give you a hint, but what you're going to notice is that random array is going to change because we've used the storage keyword, and you're going to notice that memory did not change after using this keyword. So that's just a little hint, but to sum it up, memory is non-persistent after the function runs. That data store pretty much is dropped from the contract, and then when using storage, that's persistent. That data store is kept after the execution of that smart contract. Lastly, a key thing to understand between these two is that storage is much more expensive than memory. Obviously, because the storage is having to be maintained after the execution of the smart contract. Since this memory is dropped, the contract saves much more money or fees on gas. And when you are implementing your smart contracts or building your dApps, it's just going to be important to understand when you would need memory and when you would need storage. Depending on your logic, you're going to have to customize that. All right, in this slide, we're going to talk through the importance of gas. Remember when we discussed that each execution of your contract is going to cost some bit of gas, right? And depending on the storage, depending on how big this contract is, depending on specific variables, the gas costs may vary or differ. So it's important that we pay close attention to loops and arrays, and we're going to take a look at an example here. Zoom in on that, throw that down. All right, so when we look at this loop, we see that we're iterating over a undefined length of an array. So what I mean by undefined, I mean a dynamic array. This random array of numbers can grow to be however big we decide to create, we want to make it. So in this contract, if this random array of numbers was, I don't know, let's say 100 units long, or had 100 elements within that array, the gas cost of iterating over those 100 elements would be significantly different if this array was about 1,000 units long. So it's really important as an auditor and as a developer, you take special attention towards your arrays, but also your loops, because if your array is too long, you may get specific errors in your contracts once it reaches this length. So what you may end up creating is a denial of service. It's also known as a DOS. This is when basically you cannot use a specific function or a specific operation within your smart contract. Another thing to think about is gas griefing attacks. This is a little bit more advanced if you are newer to smart contracts, but a gas griefing attack is essentially an attack when it's an attack you can make whenever a contract is making external calls to, let's say, another contract or in some relayer type of operation. When you make calls, it may require a certain amount of gas, and if this call is made and it doesn't have that amount of gas, it will fail. And this is an interesting case where you make a smart contract call, it fails, and if you don't have a fail-safe or some type of error handling for this specific case, then you have just created a bug, and that's a gas griefing attack. Now, we're not going to need to know this at this early on in the course, but it's good to introduce some security concepts so that if you're interested, you can read up more about gas griefing attacks. A very important concept in Solidity involves reverts and require statements. This also is we're going to touch a little bit on errors and some events. In Solidity, when a contract reverts, that's essentially retracing back everything that's happened in that transaction, and essentially it cancels it. Let's say your contract is performing a few operations. Let's jump into the code here, and let's say, actually, let's go to where we have our revert statement. Let's say your contract is performing some type of operation, and if a condition doesn't check out, you want to revert or cancel that transaction. That's all you're doing. You can use revert in this case. I prefer to use revert over require. There's essentially no difference between the two. They both cost the same amount of gas. Lately, you will see many developers using revert. I think it just looks a little bit cleaner. In a require statement, we can do the same thing here by saying, is membership open? And is that equal to true? And if it's not, you can have it spit out some type of error. or you can say membership close. So this is the alternative way to do it. Many people will create an error so that you can just invoke that error instead of actually having this string created here. But it's really up to you how you want to do it. Something I did leave out is there's something called assert. So these are also validation type of, this is also a validation type of method. I typically don't see assert as much anymore, but this is another avenue you can use whenever you need to control the logic within your smart contract. Another important topic we wanted to go through is events. So usually you would use an event when you want to show something critical has happened within your smart contract. Events are used for many events are used for many front-end developers whenever they're integrating a front-end within a smart contract. So let's say I have a smart contract that is an easy store. Every time someone goes to set a new number, this event will emit. Well, as a front-end developer, I may want to show whenever a user has performed some action within my smart contract. And what we can do is we can grab this event from the blockchain logs and emit that within our front end. So how you create an event is before you even start creating your functions, you create an event, you create the outline of it, and then when you invoke that event, you just call it like you would a function. And if we go on chain, see if we look at Etherscan, I wonder if we can just take a look at what an event may look like. Probably would need a contract. Nope. Let's look at Uniswap. Okay, we have our contract. Do we have any events? Okay, so see how we have a delegate changed. This event will be emitted in certain cases. And if you want to ever see what those events look like, sometimes you may have to look in a specific transaction. You have to see what happened and you have to see what logs. So these are some of the events that were emitted whenever someone interacted with a contract. So as a developer, if I wanted to see, okay, when did someone use a specific function or perform some operation within the Uniswap contract, I may look for specific events that happen and then display that in my front end. Or if I'm on part of the Uniswap team, they probably have some type of display for this event. And that's everything you really need to know about reverts, requires, errors, and events. The thing we're going to cover in this module is the difference between EOAs and contracts. EOAs are externally owned accounts. These essentially have private keys, and then you have contracts which do not have private keys. EOAs do not store data. Contracts do. As we know, because we're storing code, we're storing data on these contracts, it has to hold some type of data. And then both can interact with each other. It's very important to understand that your EOA usually interacts with your contracts, and contracts can interact with the EOA by sending fees or funds over to an EOA. Both also have public keys. That's also very important because we need to identify our contracts in some way, and that's how we do that, is we use public keys. So for example, we have deployed our contract, our Easy Store contract, and I'll go ahead and just do it again. I'm going to compile it, we're going to redeploy it, and our contract is deployed. Okay. Now this is all done locally. We're not doing this on chain. This is done in a VM. The contract address is going to be this right here. So this is the public key of the contract. You may see contract address. That's the same thing as the contract's public key. And then the from address, the one who created this contract is this account right here. This is essentially a fake EOA or fake externally owned account. So when I say an EOA interacts with a contract, let's say I want to set a number or set this number variable. I want to set this number to be 2. When I run this contract execution, we're going to look at this and we see that indeed we set this number to 2. This is a log we created or event we created. You can also see that being done here. Another interesting thing to look at is that the address, my EOA, is the same one I told you I was. The OX5B, that's my account here. And then remember the smart contract address that we deployed Oh, I was just realizing, why does that look a little different? And that's right, I deployed one earlier. So the contract address I was interacting with was the OXD. This is an earlier version, but the one we just deployed, I believe, was this OX7. So yeah, so we just deployed that. Let's actually update the number on OX7. Let's change that to 2. Contract interaction runs. And there we have it. This is my from address, my EOA, interacted with my contract address right here. Module 4, we're going to run through deployments. So we're going to talk about deployments on the EVM, a little bit about bytecode, and then also about some tools you'll be using in your development and security process. All right, so we're going to first talk about deployment on the EVM, and we're going to jump into Remix to talk a little bit about pushing your code to the blockchain, the permanent ability of, I won't say permanent ability, but the fact that once you deploy your code, this becomes permanent, and then we're also going to touch a bit on gas cost. All right, so if we jump into Remix, to first deploy your contract, you need to compile it, and once you compile this contract, you're able to then deploy it on chain. So when we come in Remix, come to the left side of the tab, we go to deploy and run transactions. If you see here, I'm running it in a VM. This is just a Remix VM. This is not using any testnet at the moment. It's a VM that's already included within Remix. And so what we're gonna do is, we already have this one deployed, but let's go ahead and deploy a new one. All right, so I deployed it twice on accident. And let's take a look at the console. All right, so we've now deployed this Easy Store contract. Here's the status that it succeeded. We have our transaction hash for the deployment and some more details about what happened when it was deployed. Now, a key thing to understand is, like I said, once you deploy something on chain, it is permanent. This is why it's a big security risk, excuse me, if you have deployed a contract and you have bugs in it. These are things that are permanent and they are immutable, right? You cannot change the state of that contract. Well, what I mean by that is you can change the storage of the contract, but the actual way the code is set up, you cannot change that. This code will always be this Easy Store contract. So that's why we really want to stress that once you deploy, it's important that you have your contracts audited and make sure that you have really foolproofed and secure-proofed the contracts. You cannot reverse this. You cannot reverse this deployment. Now, what you can do, there are interesting things like upgradable contracts, and we won't get into that as of now. But there are different contract methods you can use to make your contract upgradable. There's also something called a self-destruct, which means you can actually delete your contract But for now, with how most of the Solidity space operates, is you deploy that contract and there's no going back. So after giving that little spiel, let's talk a little bit about what does this contract look like in the EVM. So we talked a little bit about opcodes, but we want to talk about bytecodes. So this is what bytecode looks like. On Etherscan, it may look like this. Go to this exchange contract, and there we go. We have the deployed bytecode. So another thing to talk about is the fact that there's a difference between contract creation code and then the deployed bytecode. So whenever the contract is being created, that bytecode is a little bit different than the actual deployed contract code. And for those of you who are wondering, well, what is this? This is the instructions for the Ethereum virtual machine for when someone is interacting with your smart contract. This is what your smart contract looks like to the EVM, right? So whenever you go to interact with the contract, these opcodes, which is what we talked about earlier, this is what is actually happening underneath the hood. So that's a little bit about bytecode, deploying your bytecode, and compiling, then deploying your bytecode, and then getting it on chain. That is essentially what that entails. Another thing I didn't talk about is the gas cost. So when you deploy your contracts, it's actually a lot of gas. The creation opcode, to deploy your contract, it takes a lot of gas to do that. You are taking your contract and pushing it on chain. So it's really important to understand that you can't constantly deploy a bunch of new contracts. It's going to cost a lot of money. So that is a really important thing to note as well in terms of what happens when you deploy, what's happening underneath the hood. All right, so the last thing we're going to talk about is tools to use in your development and security process. So at the moment, there are two main tools that developers and security auditors use. Those two tools are Hardhat and Foundry. Now, there's a few differences in choosing the framework or tools you want to work with. With Hardhat, the biggest things to know here is that it's comprised of two different languages. So you're interacting with Solidity smart contracts, but you're also interacting with JavaScript or TypeScript to make those calls and interact with your smart contract. You write your test in JavaScript, you write your deployment script in JavaScript. It's preferred. I will say it's a preferred method for many front-end devs, and just devs in general who are building the full stack for Adapt to use or deploy things with Hardhat. There's an ongoing battle on Twitter, or at least in the security and development space. So you can choose whichever one you like the most for your development process. But with Hardhat, that's the main things to know about it there. So overall, you're interacting with not only Solidity, but also with JavaScript. Okay? So you're writing all your tests in JavaScript. You are deploying locally using JavaScript scripts. That is the main thing to understand about Hardhat. Now with Foundry, this is the newer tool that many developers and security auditors are starting to migrate to. The biggest thing here with Foundry is that this is a framework, or I'll say Solidity framework that was built using Rust. So it's exceptionally fast. And the other cool thing about it is that everything can be done in Solidity. When you write tests, your tests are done in Solidity. So many developers like this as well because it defeats the purpose of having to context switch. It allows you to essentially write all of your tests, write all of your scripts all in Solidity. So this is the cool thing about Foundry. Another interesting thing is that they have some advanced testing capabilities like fuzz testing and invariant testing. And so this is really cool. If you don't know what fuzz testing is, think of taking a bot that is able to send millions of parameters to a variable function. That's the best way I can explain it. When you fuzz test, you're essentially stress testing a function or different functions within your code or smart contract. So if you think about it, if we have in here, so we have a function that does a withdrawal. If we wanted to fuzz test this, we can perform we can deposit different types of values and attempt to withdraw that, and we may do it this like 1,000 different times. So this is a fuzz test. You're running a test 1,000 different times and trying to see what are the interesting results that this thing can spit back out. So this is a cool thing about Foundry. These are the main two tools that you're likely going to encounter on your journey. I will go ahead and say now, this course is mainly going to be written in Foundry. All of our tests and CTFs that we generate for you are going to be written in Foundry, and even the CTFs that we use that are already online and open source are going to be created in Foundry. So that's what you're going to have to get most experience and exposure to. We'll make sure we link enough documentation so you can go ahead and get started and understand how Foundry works.